Hello, and welcome to GreenValley International's latest webinar. Today we'll be talking about LiPowerline. I will be providing you with an introduction to the software, as well as a brief overview of how to operate specific workflows and tools. We have a lot to cover, so let's dive right in. Okay, we can dive right in to our LiPowerline tutorial here today. First thing you want to do is launch the LiPowerline standalone software as an administrator. Okay, we can dive right in to our LiPowerline tutorial here today. First thing you want to do is launch the LiPowerline standalone software as an administrator. The software will then load and you'll see this graphical user interface. It should be familiar to those who have used LiDAR 360 in the past. However, it's more streamlined to include only tools that are necessary to the workflows that are pertinent to LiPowerline. What we'll do is we'll add some sample powerline data. This powerline data is also included in the tutorial for LiPowerline that can be found on our website. The data I'm adding is a LiDATA file, which is GreenValley International's proprietary LiDAR file format. However, LAS files can also be imported directly into LiPowerline. Upon import, the Powerline Parameter Settings menu will pop up, and you can begin to set important fields. The first is to set your working directory. I've already done this ahead of time, so I'll navigate to the working directory folder I created and select it. Secondly, you'll want to define the spatial reference system used for the input point cloud. This is important to do because the outputs will also be in this point cloud coordinate system. You can import coordinate systems from WKT or PRJ files if you have them available, or you can look them up by EPSG code. Once you've used one recently, it will appear in this box. Here we've already have our spatial reference system assigned correctly, so we'll move on. The Classify and Detect Parameter tabs is very important. This is where you store the values that determine if a point is to be considered a danger point. It allows you to set different clearance distances. When you have many classes, it is best to import an XML file. An XML file is simply a database file that can be used to store information and different attributes for different power line conductors. We can store different clearance values for different voltage power lines. Let's choose 220 kilovolt line from the list, and then we'll go and inspect the Classify and Detect Parameters tab to see what's stored in the XML file. Here you see that there are 4 columns here. You have first, which cannot be accessed, the ID column, followed by the class, and then the detection type, and then the distance column. We'll walk through these and I'll explain to you exactly what they are. The class is essentially the type of point that will be analyzed when trying to determine if it falls within the clearance zone that must be maintained between objects and the power line infrastructure. The detect type is simply the way you measure the distance. We allow for vertical, horizontal, and space distance. Up here in these drop-down boxes, you'll see that you can change the class value for each category from the default. This is often very helpful if you get data that's already been classified from a service provider. The scissors crossing analysis will be used when you want to evaluate safe clearance distances for when power lines cross over specific types of objects, including buildings, railways, roads, unnavigable rivers, or other sorts of power lines. Let's go back to the Clearance and Detection tab and show you how you can change the actual distances. In this example, we're not going to actually be detecting any sort of violation for ground. So what I'll do first is I'll actually go in and I'll show you how to delete a row. Go up and find our ground class, click on it till it's highlighted, and then select Delete Selected Row. Now we just have the classes for which we want to detect if they're too close to the power lines and create a clearance zone violation. You can go to the distance column now and you can actually change this setting. For this illustration, we'll be setting all of our clearance distances for each vegetation type to be 12 meters. You see where there's two types of danger detection going on. You can select two different distances separated by a slash. Lastly, select the file name that you'll be exporting this new XML file as. Click OK. And you'll see that the new XML file you just created is loaded into the Classify and Detect Parameters field. Let's change the display here a bit. Let's color by elevation. And then we'll turn on EDL. EDL is a visual effects filter that allows you to discern distance, or the user to discern distance better within the point cloud. Here we have two spans of transmission power line infrastructure strung between lattice type steel towers. What we're going to do here is we're going to classify these point clouds, then we're going to vectorize them before we go on to detect danger point, produce a report of where those danger points are, and then lastly do some simulation and early warning analysis. The first step in this is to actually mark the locations of the individual towers. Here I click on the Tower Editor toolbar and I click down the line to mark towers approximately in the center of their location at the top along the two spans in our sample data set. As they're added, you'll see them populate in the table located underneath the power line panel on the right side of the screen. Here you're looking at tower number 2. You can see that its location is marked, and we can also now decide which type of tower this is. All towers in this sample data set are straight line towers, so we'll set them all to reflect that using the drop-down menu underneath Type. All this information is stored to that LiPowerline file that's in the project working directory, which is created automatically. Now in our next step, we're going to take this point cloud and we're going to classify it using a few different classification tools that are available in LiPowerline. The first method that we will use is a machine learning based method. In this method, you'll create a training data set which is then used to classify point clouds that are unclassified. To do this, we'll first select out one span of the sample data set using our polygon selection tool. Do an in-cut to keep only points falling within those polygons and save it out to a new LiDATA file. can go ahead and add it to the current project once it finishes creating. And to avoid confusion, we'll shut off the original data. Now we're only looking at the clipped subset of the original sample data. Let's visualize it by classification here. Here you see that all the points in the point cloud are currently belong to the unclassified class. If you want to see that in another way, you can always open up the Info tab for the point cloud and check to see how many classes are available and how many points are in each class. This way. The first step in our classification is we're going to classify ground. There are many tutorials on our website about using the ground classification tool, so we'll just accept the defaults and allow the tool to run in this situation. This should take a little bit of time, so be patient. However, once the tool finishes running, you'll see that a very small number of points, the lowest points in the scene, have been classified as ground. Let's change the symbology so it's easier to see. In fact, I'll shut off the unclassified so you can just see the points that have been classified as ground points. This looks like a good result. I can see there's a road bed down there where I expect it to be. Seems like it's caught some of the undulations in the landscape that I anticipated being there. So I'm happy with this. And I'll turn back on my unclassified color, which is green, and move on with the next stage of creating a sample classification training data set. What I want to do is take points belonging to this unclassified class and classify them according to vegetation, conductor, and tower. I'll use the 2D classification editor tool, or profile tool, to draw a line that is perpendicular to each tower and parallel with the direction of the lines. You see that in the first step there, I converted all points along that gap to being classified as conductors. In this process, I captured the towers as well. But I feel like it's easier now to just select points from the conductor class and reclassify them to be structure, which in this case is tower. This will take some time, so please just watch and notice the techniques that I'm using to classify this point cloud manually. As I get to the bases of the towers, I notice it's quite hard to tell what points belong to footings, what points belong to the tower itself, or what maybe belongs to surrounding vegetation or land. So I'll have to use my best judgment here. In a working scenario, I would probably draw more profiles and zoom in and take more care to make sure that I was only selecting points which most definitely belonged to the tower of the structure itself. In this instance, I'll also be classifying the hanging insulators as being part of the tower structure. What I could also do is have another class available for insulators and classify these sections of the point cloud more appropriately. You'll see at the very top here where this guy wire, or excuse me, where this shield wire or ground wire is attaching to the tower, there are no insulators. I'll now move down to my second tower on the span and repeat the process where I'm classifying the steel lattice structure of the point cloud to be as tower and also the hanging insulator portions as well. This one's a little trickier when I get to its base of the tower because there's a lot of vegetation. So I'll use this trick where I look from the top down on it and then attempt to just draw a box around what looks like the break between actual tower infrastructure and surrounding vegetation. Once again, had this been for a real project and not this webinar, I would have taken much care to make sure that I was only classifying points that belong to the power tower. So now I have the point cloud, or at least the training data, classified in such a way that I'm ready to move on to the next step. In this, I'll input the training data point cloud I just classified manually, and I'll create a statistical model that will then be used in subsequent machine learning classifier operations. I'll call it training data model, and I'll click Save. Click OK, and this will run the classification. It will take a bit to finish, but when it does, I'll be able to go ahead and classify the sample data set using the statistical model. It's doing it in sections. Each section, or span, represents the space between two towers. Once the process is finished, you can click OK, and then you can go ahead and remove the original sample data, which you see is unclassified there, and turn on your training data. You see here these two LiDATA files. These are the outputs of the machine learning classifier. If we turn them off, you see just the training data, and then we'll turn off the training data so you can take a look at the results of the machine learning. The span that's circled here in the yellow box is the one that was classified using the training data set. It appears to have a little bit of misclassification error going on, where the lowest set of conductors on this span has been classified as unclasses, where we can see it obviously belongs to the class conductor. So we can use a few different tools available. Here I'll use the 3D classification editor, and then I'll save the result before closing out of the editor and moving on to the next step. Obviously the first span is well classified, or I should say the other span, because this was in fact the span that was used as a training data set. And there you have it, your machine learning based classified LiPowerline data set. However, we actually want to detect danger points for classification and not unclassified portions of point cloud. So we can use this classify by attribute tool to quickly transfer all points in the unclassified class to the low vegetation class. I'll make sure that both the LiData files for each span are selected and run the tool. You see there in the classes legend in the lower left of the viewer that 3 is, or green is low vegetation now. Also in the info you see that unclassified points disappeared and an equal number of low vegetation classified points have appeared. The final thing I want to show you is how you can actually change the name of a class. Under Display and then Class Setting Options, you can get a list of all the classes that are available or bins in which you can put a point. Here, let's change shield wire to ground wire. Simply double-click on the name, and then the setting class name box will pop up, and you can retype in the new name. Click OK, and the name will be kept. Here, we'll say that the topmost set of wires on each power line span are ground wires. So we'll go ahead and use the 2D classification editor or profile tool to actually rename these points to belong to the ground wire class. And we'll only select points that are currently labeled as conductor, so as not to disturb the tower points as we do this. We'll zoom in to the point cloud and then use the polygon selection tool to pick out individual spots along these two spans that contain points which should be classified in this instance as ground wire. I'll continue to go along until this is done. As you can see when I zoom into the tower, because I didn't select structure, only those points which had previously been classified as conductor were reclassified as ground wire. Once I'm done with this and I've saved my result, I can close out of the 2D classification editor and admire my handiwork. In part 3 of this tutorial, I will go on to vectorize the power line infrastructure assets themselves. In this example, I'll be creating 3D models of the hanging insulators, the towers, the conductors, and then exporting them out as shapefiles for further analysis and later use. First, I'll change the colors of my conductors and my structures. I'll change the color of my conductors to add more contrast to my structures. I also will figure out what is the length of the hanging insulators that I'll need to add. I've determined it's 3 meters here using the length measurement tool, and I will now click the point where the hanging insulator connects with each conductor bundle. Here you see I've misplaced one of the hanging insulators. I can simply use the select tool, click on it, and hit delete. Relaunch the hang insulator tool and go on vectorizing this power line infrastructure asset type. I can also use the current tower index button to tack through all of the different towers without having to manually rotate or adjust the point cloud in between towers. This saves me a lot of time and really accelerates the process. By turning off the conductor and the structure points, I'm able to see the locations of the hanging insulators that I vectorized. I'll check to make sure that I don't have duplicates and that they all seem to be in the right spot. Once I've confirmed this is the case, I can close it down and I'll turn back on both my conductor and my structure points. I can save this set of attachments as a text file for later use. Next, I will go ahead and vectorize the actual conductors themselves. Here I'll use the batch vectorization tool and accept the default. The batch fitting power lines tool runs quite quickly, and when it's done I can turn off the conductor points to see the green lines that are now the vectorized conductors. Now the last type of feature that I'm hoping to vectorize here for you today, and that is the power towers themselves. I'll launch the tower editing toolbar and then choose to create a tower from 5 points. This tool allows me to select the 4 base points of each tower as well as the high center point, and from these 5 points create a tower structure. Finding the high point can require you to rotate the point cloud. By turning off the structure, I can now see that I have 3 types of power line infrastructure assets vectorized. I'll add the tower cross arms to make a 4th. In this instance, I'm placing the tower cross arms just between the hanging insulators that I created before. And here I have it, my final 3D vectorized model of a power line infrastructure, which includes conductors, a tower, and hanging insulators. I can save this tower file for later use. I can even load it back into this demonstration and use it to vectorize other towers located in the sample dataset. I'll turn back on my structures so I see exactly where the high center point is that I'll need to place the tower object. Once again, I'll need to rotate the point cloud to find it, and this can take a little doing. Once I've found the center point, I can use the Place Tower icon to drop the tower structure that I have loaded in the tower file. Here I only have one type, so I can accept the blank drop-down and click OK. Had I had more than one type of tower in the tower file, then I would have to have selected it there. Finally, I'll place the tower that I vectorized at the end of the second span here in our sample data set. I'll open up the tower file, and then use Place Tower, click the high center point, accept the blank default drop in the drop down, click OK, and there I have it, my 3D vector model of this sample data set. These vectorized models can be very important when trying to do analysis on point clouds that are very sparse. One such analysis that we'll move on to now is danger point detection. Danger points, as already have been defined, are areas in the LiDAR point cloud where objects have crossed a safety threshold. Identifying these objects is of great importance during inspection. LiPowerline offers a danger point detection toolset which automatically finds these areas and then logs them to a database for you to inspect and eventually produce a report from. As inputs, the safe distance thresholds are defined by earlier steps that we took during the initial setup of the project. Things such as cluster threshold and max cluster range depend on the nature of the input data itself. In this situation, we'll ignore the vector file and simulation file because we're going to be doing this analysis based on the point cloud, and we can hit start for it to run. The tool takes a minute to operate, and will detect danger points along each of the spans included. Then you see in the PowerLine tab on the right, after the tool has finished running, a list of the detected danger points. You can click on any of the points to see where it's identifying a danger object in the scene. 4 danger points identified in this data set. I now may wish to take my analysis a bit further and produce a report that can then be handed off to a client, a utility forester, or an arborist who's going out to perform the mitigation procedure. To do this, I will first load the danger points that I want to include in the report. Here I only have these 4 available, so I'll keep them. And then in my next step, I will generate an image. The image generation shows figures in the exported report. There are many different parameters one can set, but for now we'll just accept the defaults and start the render image tool. Once these images have finished rendering, we'll be ready to generate the HTML report. We'll put in the spans or the data files for which we wish to include in the data port, and then we can also add in information that is relevant to the company or the service provider who's completing this report for an inspection. Choose the output path. Here we'll use our working directory and create a special folder called Report. Click Save, and then Start to run the tool. The report will generate quite quickly and be loaded into your browser. You'll see you'll have a key for the classification, as well as the images that were rendered in LiPowerline. The images show the locations of the danger points between specific towers, as well as their latitude and longitude coordinates. Click OK when the tool is finished to clear the screen. And you're now ready to move on to the next stage in our analysis that's included in this tutorial, and that's the simulation of impacts of weather on power lines clearance zone. Weather can cause power lines to sag, expand, contract, and therefore it's important to understand how this affects the safe clearance zone. LiPowerline allows you to import your vector objects created in previous steps, including the conductors themselves, as well as the insulators that were attached to them. Users can find the output path file that the LiSim file will be stored in. A LiSim file is a simulation file that can be used in other analysis carried out in LiPowerline. I'm going to name the LiSim file simulation and click Save. Now I can enter in the scanning conditions that were present at the time of data capture. When I captured this data set, it was 15 degrees Celsius outside, there was no ice on the wire, and wind speed was 0 meters per second. However, I want to simulate how the extent of the clearance zone would change when the wire temperature dips to minus 10 degrees Celsius, ice thickness increases to 10 millimeters, and wind speed increases to 10 meters per second. I'll click Start, and the process will run. When it's done, you can click OK, and now you can add the vector outputs of this analysis to LiPowerline and visualize them in 3D. They'll be stored in a shapefile, which is called here Powerline Simulation. Here in this image you can see there's a cayenne blue solid line beneath the yellow points that are labeled as conductor. This indicates that under these conditions the power line would have some sag, which makes sense given the ice loading that was observed. This means objects that are on the ground at the threshold of exactly 12 meters may be pushed into a clearance zone violation under these specific conditions. This illustrates why it's important to rerun danger points detection tool after the simulation file has been produced. Another form of early warning analysis, which can be of great use to managers of power line infrastructure, is the tree fall analysis tool. The tree fall analysis tool is quite complex and deserves its own tutorial. For this, we'll run it based on the simulation data that we just created in the previous exercise, which represents ice loading, wind, and cold temperatures. We'll keep our safe distance referencing the XML file created much earlier in the tutorial before clicking Start to run the tool. Notice the data type radio button before I hit Start was based on simulation data. Thus, we had to enter the simulation file in the bottom field. After it's done, you can click OK, and you'll see in the Power Line tab on the far right the locations of tree fall hazards along the spans. Similarly to how you did with the danger point detection, you can produce a danger report that can once again be handed off to a client or internal personnel. The ability to simulate future conditions or past conditions, as well as understand how threats may arise in the future, is a powerful feature of GreenValley International's industry-specific solution found in LiPowerline. The way tree fall analysis works is it actually segments the point cloud, or the vegetation in the point cloud, individual tree objects. This allows you to identify exactly which tree it is within a forest canopy that needs to have the work performed on it. It'll also give you some idea of how large the tree is and how large the crown is, what access to the crown can be like, and other pieces of logistical information that can be important to have on hand when planning to carry out the work. And that's going to be all we have time for here today, folks. Please be sure to post your questions and comments below, and check out our tutorial for LiPowerline. Remember, you can email us at info@greenvalleyinternational.com to request a trial license of LiPowerline software. Thank you, and have a good day.